Better like this, yeah. All right. Hello, everybody. I'm Norswap. I do research and development at Optimism. And what I want to talk to you about today is how we secure the Optimism blockchain. So Optimism is a layer 2 rollup. So first of all, if you're not familiar with rollup, I'm going to give you the real short version of how an optimistic rollup works. So the issue with Ethereum is that it doesn't scale. It doesn't scale for a very good reason, is that they want to stay decentralized. And so sort of the line in the sand that was drawn is that everybody should be able to validate the Ethereum blockchain at home using only a laptop and maybe some extra equipment, but it should stay relatively affordable and hassle-free. And that's pretty good, but we still have a problem that people want to transact and there's not enough transaction space available. So rollups are a way to fix this, and the way rollups works is that you have your L1 blockchain, so that those are the little computers you see there. And if you're a L1 user, you're rich, so you have a top hat and a mustache, and you can transact directly on Ethereum. If not, you're L2 user, you can transact with one or multiple entities known as the sequencer. And sequencers are big entities, and there will be much less of them than L1 nodes. So what the sequencer do is that they process the L2 transactions, just like they were normal transactions. Then they send the data of the transaction to L1. Only a transaction, these transactions are not executed on L1, they're only executed on L2. They also send to the L1 blockchain the result of executing the transaction. So that's a state root that commits to the whole state of the layer 2 blockchain. Then you have these other actors called verifiers. And what the verifiers do is that they download the L2 transactions that have been posted to Ethereum. They re-execute them. And then they check if the result that they get is the same as the result that the sequencer got. If they get the same result, it means everything is fine and the sequencer did a good job. If the result is different, it means that there was a bug in the sequencer or the sequencer attempted to do some malicious action to steal funds or something like that. So if they detect such a case where they disagree with the result of the sequencer, what they can do is something called a fault proof. So this is a process in which on Ethereum, they are going to challenge the result. And this presentation is really about explaining how this fault proof process works. How can we be secure, right? So there is one, compared to Ethereum, it's almost as secure. There's only one security assumption that is added. And this security assumption is that there's at least one verifier that exists that is honest. You only need the one, and then you're fine. Okay, so the next step is explaining these fault proofs. So as a recap, optimistic rollups are secure if Ethereum is secure, and we rely on this single verifier. The fault proof is played through something called a challenge game, and it's played between two actors, a verifier and the sequencer. We also sometimes call them challenger and defender, but for simplicity, you can think of them as the verifier that detected the problem and the sequencer that posted the result in the first place that is being challenged. So the guarantee is that as long as Ethereum itself is secure, then this process will work, and then the challenger will always be able to challenge the sequencer successfully, assuming he is indeed right and the sequencer misbehaved. And so if you given this property, it means that using the main bridge of Optimism, you will never be able to transfer stolen funds back to Ethereum. So this is the same thing, but in a graphical way for those of you that are more graphical. So you have L1, Ethereum. The verifier reads the batches, so these are groups of transactions, of L2 transactions. He executes them and creates these output routes. He also downloads the output route from L1. Then he compares those. If they're the same, everything's peachy. But if they're different, then it does this challenge game, this fault proof on L1. So now we run into a problem. So we have determined that executing the transaction leads to different results for a sequencer and a challenger. How do we decide who's right and who's wrong? You know, if you were to take a naive approach, what you want to do is re-execute all the transactions on Ethereum. The problem with that is that it's extremely expensive. So the very simplest approach you can take is to rerun the block on Ethereum, so in an EVM interpreter that is itself running on the EVM. There are huge overheads in doing so, and it's not possible because you're executing a whole block worth of gas within a transaction that is itself limited in gas. And because you have overhead, so a multiplier in the time of execution, it's just not possible. So another solution would be to say, well, blocks on layer 2, they are actually EVM, right? Like on the optimism, we use the EVM. And so the code that we're executing is the same that is being run on L1. So what if we could just execute that code directly? That's a good idea, but there is a problem. The problem is that there's a lot of opcodes and operations that depend on the context of the blockchain. And so a very simple example of that is the block number opcode. So when you run block number, on L2 you will get the L2 block number, but on L1 you will get the L1 block number. And so there is a way to fix that, and it's that you need to patch the opcode to remove this and put a call to a contract that holds all the context. And you run into similar issue if you're trying to read the blockchain memory, for instance. This is still way too expensive. But what if we did this, but instead of challenging a whole block, we would just challenge a single transaction? So this works, and this is what Optimism tried to do the first time we tried to do fault proofs. We tried to do exactly this. There are a lot of nasty issues with this. It's still expensive, and to give you just an example of one nasty issue that happens with this, so Ethereum has a limit on the size of contracts. So the number of opcodes that you can put in a contract is bounded. And the problem is that we need to patch the opcode. So we take the L2 contract and we replace some opcodes by some calls to special context contracts on L1. And these patches, they are bigger than the original thing that we replace. So the contract size grows when you deploy it on L1. And that means that effectively, your L2 contracts are much more limited in size than the L1 contract. So this is a very, very bad user experience because you try your contract, on L1 it works, but on L2 it doesn't work because it becomes too big. So this was very nasty. So what is the solution? It's to use something called a challenge game. So now we're stopping with the idea of executing the whole block or the whole transaction. What we want to do is figure out exactly where we disagree in a small part of the computation, and then we want to execute only that small part on Ethereum. And so well, we will call this a single step of disagreement. So the goal is to find the single step of disagreement. And what is a step? There's different ways you could do it, but the two most common ways are one EVM instructions or one assembler instruction in the program that validates a block and executes the transactions. I'm going to explain both of these things. So our fault-proof and challenge game system is called Cannon. It was originally designed by George Hotz, who was a very famous hacker. He was the first one to unlock the iPhone, and he also hacked one of the PlayStations. And now it's under development by Optimism, so including me. It's not the first system of this kind, so Cardizy does something different, Arbitrum, also think TrueBit. So this is an idea that has been around. It's the idea of verified computation. So you do off-chain computation and then you verify it on-chain. However, it is the first system of this kind that supports EVM equivalence. So anything that works on Ethereum also works on optimism. You can reuse all the tools, Hardhat, Foundry, whatever you use to do your development, it will work on optimism out of the box. So to figure out where we disagree, the challenge game performs something that is called, for the full proof, you do something called a challenge game. And what a challenge game is, really, it's a bisection on the execution trace. So what is the execution trace? When you run a program, you run a bunch of instructions one after the other. And the execution trace is just the list of all the instructions that you're going to execute. So, but what's being executed? So there's two ways to do it. You can think of EVM execution, then your trace is a bunch of EVM opcodes. But validating a block is more than just executing transactions. And so if we go this way, where our trace is EVM opcodes, we need to do the rest of the block validations in specialized EVM contracts that we have to write. The other way to do it is to say, well, the program that we execute is not the EVM execution of the transactions, it is the validator software. So Go Ethereum or Aragon, all those, they validate blocks. So what if we could take those software and run them, and that's our execution trace, and that is what we'll be able to challenge. And so that's the approach that we're taking, and we have this piece of software called mini-geth. So it's a subset of Geth or Go Ethereum that is patched to support our system and compiled to MIPS. And the difference between Go Ethereum and mini-geth is very, very small. So we just removed a bunch of codes, that's very easy, and then we made like a very small amount of changes so that it supports the system. And that's important because it means that whenever Go Ethereum is updated, we can always update mini-geth very easily. So how to figure out the step of disagreement over this execution trace? The general principle, and I'll give a graphical illustration of this after, is that you want to hash the memory of your program at different points of the execution trace. And you're going to start at the midpoint. So at 50% of the execution, after half the opcodes, you take your whole memory, you create a hash of it. So for those of you that are familiar, there's actually a Merkle root. And you send that to the L1 challenge contract. The verifier does this, the sequencer does this, and they compare the results. If the results are the same, we go to 75% of the execution trace. So that's like half of the remaining span. And if it's different, it means that we disagree before, and so we go to 25%, right? So if you agree at 50%, it means the disagreement is after. If you disagree at 50%, it means the disagreement is before. And we can keep doing this, cutting the space of possible disagreement in half each time, until we find a single instruction where we agree on the memory before, but we disagree on the memory after. So executing this single step against the memory will tell us who is right and who is wrong. So once we find this step, we need to execute it on the blockchain. And so we compile mini-geth to the MIPS instruction set, and we use MIPS because it's a very simple instruction set. So we have an on-chain MIPS interpreter that is less than 400 lines of solidity. And we use that to execute the instruction. But this instruction will need to access the mini-geth memory, right? And the mini-geth memory is not on layer 1. It also needs to access the transaction batches, and those are on layer 1, but they need to be accessed. So accessing memory is relatively easy because we already have a hash of the memory. We have a Merkle root of the memory, and this Merkle root lets us prove any possible piece of memory against it, right? So a Merkle root is a tree structure made of many hashes, and the property of it is that you can say, well, this byte is this value, and you can submit a proof of that you can verify on-chain. And a single MIPS instructions is not going to touch a lot of memory spots, maybe 2 or 3 at most. And so you only need to provide 3 of these proofs, which are relatively small, to be able to execute the instruction. So to access the batches, and I should have said, these transaction batches, they are posted to Ethereum, but they are not stored in the EVM memory, because that would be too expensive. Instead, they are posted as call data, so they live with the transaction, within the transactions. And to access them, we use something called pre-image oracle, and this is what I will explain next. This was already like a lot of content, so I want to pause to see if there's like any questions, or there's no stupid questions, so don't be afraid. I know I look very intimidating, but I'm very nice, I swear. Everybody all right? If you're really too shy, you can come find me afterwards and ask your questions. So, all right, this is an illustration of the challenge game graphically. So, these boxes on the top and the bottom, these are the execution trace of the challenger and the defender. So every single box is one assembly instruction. So you start at the middle, you are going to take a hash of your memory, you submit it to Ethereum, and you compare. In this scenario, we're going to say it's the same. So the disagreement is after the midpoint. So you go to 75%. Again, you take a hash of the memory, you compare it. In this scenario, it's different. Again, you cut it in half, 62.5. And you keep doing this until you find a single instruction that you disagree on. All right, so the next thing we need to talk about is the pre-image oracle. And this is the way, the pre-image oracle is a way in which you can access any data on the Ethereum blockchain ever, and you can prove that this data existed there. So how does it work? So the interface of the pre-image oracle is simply a function that, given a hash, returns a pre-image of the hash. So the pre-image of the hash is the thing that needed to be hashed to produce the hash. And so assuming that you implement this in a contract, so it's very important to say that if you're using a cryptographic hash, it's normally impossible to do this. You cannot take a hash and find the pre-image, because there are many possible pre-images. And also it's computationally infeasible. But if you give the pre-image in advance to a contract, then you can query these pre-images that you've stored, say, hey, here's the hash, give me the pre-image. Why is this useful for us? It is useful because in Ethereum you get a lot of hashes that commit to important information. So you have an opcode that gives you block hashes, and a block hash is a hash of the block header, which contains useful information. Each block header contains the hash of the previous block header. So that's also something that you can use. And so using those, you can already see that if we have the pre-image oracle, we can walk the whole blockchain backwards. By starting with the hash, we get the header, then we can walk, we have the hash of the previous header, so we can walk there, then you have the hash of the previous header, so you could just traverse the whole chain using only this simple interface. So I already see that's quite powerful. And the other thing you can do is you can prove any state in any block, so any state that the Ethereum blockchain had over all the blocks, or any transaction that was ever included. And that's because every block header has a Merkle root for all the transactions in that block, and a Merkle root for the whole state of a blockchain in that block. So you go to the block you want, and then you find the Merkle root for the state at that time, or for transactions at that time, and you can go down there and prove via the pre-image oracle any state. And this works because a Merkle tree is a tree of hashes, and there will be the next slide will show this graphically, so it will be a bit more understandable. Okay, access and annual one data. That's what I just said. Okay, so this is the graphical slide. So these two trees at the bottom, these are Merkle trees. And the way a Merkle trie works, so this is a binary Merkle trie, so each node has 2 children. And basically, each node can be represented by the hash of its children. So if you start from the bottom with pure data, right, you can see that you have a piece of data L1, so maybe this is a transaction. And the node hash00, that's just the hash of the data L1. But then to create the node hash0, you hash the 2 children hash00 and hash01. And these 2 are only hashes, right? And then to create the top hash, you hash hash0 and hash1 together. And so you can see it's a tree of hashes all the way down. So to take an example of walking this, so say I'm interested in getting a transaction or a transaction batch that lives in block 41. Say I'm at block 42. I use the block hash opcode to get the latest block hash. Then each green arrow here is a use of the preimage oracle. So I have the block hash opcode. I use the preimage oracle to get the block header. Then from the block header, I get the hash of the previous block. And I use the preimage oracle to get the previous block header, so the block 41. In block 41, I get the transaction Merkle root. And I use the preimage oracle to get in the tree and get the children, and then for each children, I each time use the preimage oracle to get the child until I can get the transactions that I'm interested in. And this is exactly what we use to read those transaction batches that contain all the L2 transactions. So concretely, in minigeth, which is our re-implementation of the or modification of Go Ethereum that validates block, we use this to re-implement the database, right? So normally if you have a Go Ethereum node, it has a database of the whole state of the blockchain, of the blockchain you're validating. And it turns out you can use the preimage oracle to re-implement that. And we actually have 3 implementations of the preimage oracle, and this is where it gets a little bit tricky. It's implemented on-chain, and this is used for the single-step execution. And on-chain, we simply submit the preimages and store the hash to preimage mapping. Very simple. It is. We also have one implementation of this in that we compile to MIPS, and this one is necessary. So we need to run minigeth in MIPS off-chain because we need to hash the memory for the challenge game. Otherwise, we need to run MIPS off-chain, but we need to get these hashes so we can do the actual challenge game. And these uses prefetched hashes. So the preimage oracle is similarly like we already know the hashes in advance, and so we just read from a hash to preimage mapping. But then we also need to run minigeth in the, normal instruction set, whatever runs on your laptop or server. And for those, we need to get the preimages, and we use the JSON RPC methods that online nodes expose. In particular, we use get block by hash, and we use this thing called ETH get proof, which we use very creatively. There are some challenges there. But basically, get proof gives you a Merkle proof or of any piece of state in Ethereum. All right, so a small summary. Optimistic rollups are secure as long as they're on one less validator. The validator, if it disagrees with the sequencer, can initiate a fault proof using Canon. That's our fault proof system. So the validator and sequencer, they play a challenge game, and they find a single step of agreement in the execution of the validator, which is compiled to MIPS. So this is called the challenge game. And finally, the single step is executed on-chain, and we can access the memory of the validator through some Merkle proof, and the batches of transactions that are being executed can be read using the pre-image oracle. And yeah, that's how it works. Oh yeah. Final slide, very important. Where are we with this? So this is actually not fully implemented yet. This is the design. The design is fixed. We know how to do it. But George gave us a prototype which allowed us to challenge L1 blocks on L1. This is useless because by definition, L1 blocks are correct, right? But it's a proof of concept that shows that this can work. And so what we're almost done with is changing L2 blocks on L2. So it's a simple transposition of this concept, but it shows that whatever changes we made to the original Go Ethereum that we're using on Optimism still doesn't break the system. And then the real thing that we want to do is challenge L2 blocks on L1, right? That's the whole point. And for doing this, we need to add something called L2 chain derivation to Minigeth. And that's the part where we take these transactions that have been posted on L1, so the L2 transaction on L1, and we create blocks from them. And that's a logic we already have written, and we can import it fairly easily because everything in this stack is in the Go language. So we can use the Go module into our node directly to do that. And so this will be probably our next focus after we release Bedrock, which is the next version of Optimism. There you go. If you have any questions, again, feel free to ask them now or find me later.